Which of the following is a horizontal asymptote for the following curve? So our curve is y equals, and then on the numerator, 4e to the 3x plus 6e to the 2x plus 4e to the x plus 5. Downstairs, 2e to the 2x plus e to the x plus 1. And our choices are y equals 1, y equals 2, y equals 3, y equals 4, and y equals 5. Answer is, which one of those is an asymptote?
B.
Answer is E. Y equals 5. Now why does 5 work? Well, as you go to negative infinity, the exponential function gets small. So all the terms go to 0 except the 5 upstairs, the 1 downstairs, which is 5. So y equals 5 is a horizontal asymptote. But boy, it's really tempting to say 2. And why does 2 not work? Well, you have to look at the rates of growth. It's growing like e to the 3x upstairs and e to the 2x downstairs. So the upstairs is growing much faster than the downstairs. Now, if you're not convinced, divide everything by e to the 2x, and what you end up with is 4e to the x plus stuff. Upstairs, downstairs you end up with 2. It's getting giant over 2. Well, a giant number over 2 is a giant number. So it blows up. So you have to be careful. We know. A lot of people are like, oh, leading coefficients, 4 divided by 2, and I'm done. We know. Because we know how you think. We programmed you. But because we programmed you, we also know how to catch you. So we will put very tempting answers in. So don't just give in to temptation. Think about it a little bit. You know, thinking is very encouraged in all your courses, but particularly in math. All right. So today, we're going to have a series here. This comes from a book by a mathematician named George Polya. He wrote a book called How to Solve It. And there were 4 steps to solving problems. So the very first step, if you want to solve a problem, is you need to understand your problem. And I know people are like, what? That seems obvious. We always understand it. But I'm not so sure that that's true. So I'm reminded of a comic I once saw. A drawing. I couldn't find it, so I did my best to reproduce it. Keep in mind, I'm not an artist. But it was somebody giving a presentation to a large room. A room perhaps somewhat not too dissimilar to this room. And the audience is looking on, saying, what are they doing? What are they doing? What are they doing? And the person giving the presentation is, what am I doing? You know, it's like, nobody's really sure what's going on. Well, things similar to this happen when we're grading exams. We look at our students' responses and we start thinking, what are they doing? They're just like randomly doing something that makes no sense at all because they didn't understand the problem. So they just said, I'll just do something random. Maybe I'll get it right. No, you won't. You got to make sure you understand. So what do I mean? What are you given? What are you told? What are you trying to find? Do you understand all the terms used? Do you know what things mean like perpendicular, parallel, tangent? Do you understand these words? Can you draw a figure? So when you're thinking about, okay, how do I go about solving this problem? Step 1, make sure you understand it. And keep coming back. We'll go through all 4 steps sooner or later. All right. Well, today we'll start. We have a basic motivating picture to help us get started. So suppose we have the following. We have our scenario. We have some curve. Let's say it's y equals f of x. And we are able to find secant lines. In fact, we're really good at finding secant lines. Because secant lines mean I touch the curve at 2 points, or like I cross the curve at 2 points. So I have a point A and I have a point B, and there's my secant line, touching at both A and B. But we're really interested in understanding the tangent line. Now the tangent line only happens at 1 point. And so tangent, it comes from the word touch. So it's just touching, just barely at just one single point. Now, we have sort of our challenge, which is to say, okay, what are we trying to find? Well, we know that the slope of the secant line, we can compute that as f of b minus f of a over b minus a. So this is our slope of our secant line. And we gave this a name. We call this the average rate of change. All right, so we can find that. But what we'd like to do is we'd like to find the slope of the tangent line, which is giving us the sort of the instantaneous rate of change. Now, what could we do? Well, we had a bad idea which says, look, I have the point A, let's just plug it in, B equals A. F of A minus F of A over A minus A. But what does that lead us to? 0 over 0, which is more work. And we had to sort of do a side detour to say, well, what does it mean, this more work thing that you're talking about? Well, that's where limits came into play. So we say, okay, we can't just plug in B equals A. So what can we do? Well, the idea is to say, well, look, what if I move B a little bit? So then I'm a little closer. All right, but what if I move B again? And then I'm a little bit closer. So as I move B, what's happening to my secant lines? My secant lines get close to my tangent lines. So my slope of my secant lines get close to the slope of the tangent line. So what we'll do is we'll let B go to A, and that's what limits are. What happens as B goes to A? And so what we'll do is we'll give this a name, and we call this f prime of A. So this is your slope of your tangent line. And also, it's your instantaneous rate of change. How fast is the function changing right at that moment? Really what you're doing is, the whole thing is, it's just saying locally your function acts like your tangent line. And so we have that expression. All right. Now this is one way to think about the definition of a derivative. I guess I should say that f prime of A, we will sometimes call this the derivative. And we'll talk more about this over the next few days. So the derivative of the function f at A. Whoops. Supposed to be quote marks. Okay, so that's our goal. Now, there's two variations for limits. There's another variation, which is the following. This is the limit as h goes to 0, f of A plus h minus f of A over h. Now, what is this A plus h? Well, what you're actually doing here is you're thinking of h, it's just moving a little bit. So h is your distance you move away. So A plus h, so if I'm at A and I move h, that's your B. So this A plus h is acting like your B. And then this h downstairs, this is acting as your B minus A. There's two formulas. Between the two of them, this will be your go-to formula for probably 95% of the time. Now, you might be saying, why? Aren't they the same? They are the same. They give you the exact same thing. But there's something about the second formula that's helpful. When we come back to this idea, 0 over 0, we talk about more work. What does that more work usually look like? When we talk about, you get 0 over 0, it's like, okay, I've got to do more work. What's the work? Sorry, what? Yeah, right. So the more work is you're trying to get cancellation. That's what you're doing. So here, what makes this very nice is if you have an h downstairs, the idea is, okay, factor an h somehow out of the upstairs, and then you get cancellation. Now that's not 100% true, but that's like 95% true. So this is your more work. Now, the reason that this becomes easier, it's easier to say, how can I pull an h out of the top, than it's to say, oh, how can I pull a b minus a out of the top? So that's why this is a much more convenient expression to work with. All right, so that's our basic idea. We should try some examples. Oh, yes. I want to do a quick detour. This is going to be a silly detour, but we have to take this detour because inevitably questions arise. F of a plus h. We should talk about this for a moment. And let's pick a fairly simple benign function. Let's suppose we pick our function, let's say f of x is x squared plus x. Is that simple enough? Everyone's like, yeah, I can handle x squared plus x. Okay, I'm going to ask a series of questions. What's f of 1? Okay, 2, but what would you do? You'd plug in 1, right? 1 squared plus 1. How about f of 17? 17 squared plus 17. All right, f of t. T squared plus t. How about f of a cat? Cat squared plus cat, right? Whatever you have here, you just follow the rule. This is a rule. It says, whatever you plug in, you square it, and then you add it back to itself. So what does f of a plus h look like? A plus h squared plus a plus h. All right? So it is not, f of a plus h is not f of a plus h. Don't make that mistake. We don't want you to make that mistake. That's a terrible one to make. So just remember, whenever you're plugging in, just whatever you plug in, everywhere you see x, replace it with what you're plugging in. And then life is good. Life is wonderful. Okay, so let's try this with a function. And we don't have a lot of tools, but don't worry. Tools are coming. We're going to have great tools. By this time next week, we'll just be like, wow, look at all our awesome tools that we have. All right. Does anyone have a favorite function? Relatively benign? Maybe a quadratic. What?
X squared plus 3x minus 7.
X squared plus 3x minus 7. All right. That seems like a fun function. F of x equals x squared plus 3x minus 7. Okay, and let's find f prime of 2. Now, I'm sure there are people here who are like, aha, I could tell you f prime of 2 with hardly lifting a finger. Yes, I know you can. And we will too next week. But today, we're not going to do it the slow way. We're going to do it the long way. Only by doing it the long way will we appreciate the short way when it comes. Okay, so what do? We say, hey, there's a definition. So we pull out our definition. It's the limit as h goes to 0, f of 2 plus h minus f of 2 over h. So this is just something you know. Now I should tell you, and I didn't say this before class started, but if you were to grab your handout sheet, you'll see that there are problems on the back from old exams. And not unusually, you'll see problems saying, use the limit definition of a derivative. And no, anything that's not using the limit definition will get no credit. So you better know the limit definition because they love those types of problems. I would say there's probably a good 80% chance that the exam will have one of those types of problems. So, all right. So that's just the definition. So far, all we've done is definition. Good. Definition. Now, what do we do next? We say, well, what is f of 2 plus h? So we say, okay, we're going to follow our f of cap mentality. We're going to use parentheses because parentheses save points. Everywhere we see x, we put 2 plus h. So we get 2 plus h squared plus 3 times 2 plus h minus 7. Then we're going to subtract. Plug in 2. Everywhere you see x, put a 2. 2 squared. 3 times 2 minus 7. And downstairs is h. All right, so the first step was definition. Second step, plug it in. Not too bad. You'll notice we keep the limits. That's important. You might say, would they really take points off if we forgot to write down limits? Yeah. They're very particular about their limits. They love their limits. Okay, what comes next? Okay, so we need to work on simplifying. So essentially our goal is right now we can't just plug in h equals 0. We're going to end up with 0 over 0, guaranteed. We know in the back of our head, our real goal, our whole goal for right now is we want to cancel that h. So somehow we're going to have to extract an h from this part upstairs. We're going to have to pull it out. We're going to say there's an h out there waiting for us to extract. So we start thinking about what kind of tools we have. What are some things we can do to this upstairs expression? Simplify by doing what? Well, we can add, but in particular, we can expand, right? So it's algebra, algebra. Okay, 2 plus h squared, that's 4 plus 4h plus h squared. Distribute the 3 through. 3 times 2 is 6 plus 3h minus 7. Then we're going to subtract. And the subtraction goes through. So we're going to have 4 minus 6 plus 7 all over h. What can we do now?
Add like terms.
Yeah, we can combine terms. And if you've lived a good, clean algebra life, what should happen? You should get lots of cancellation. In particular, if there's not an h attached, you should hope that you get cancellation. And you do. So this is one of those things where there's a process here, and if you get to the end, it's like, wait, I'm not able to do my cancellation. It's like, oh, I made a mistake. I'll go back and fix it. Here we have 7h, 4h plus 3h, and then we have an h squared over h. Well, what can you do upstairs? Pull out an h. And the name of the game is we're trying to get an h from the upstairs so that we can cancel the downstairs. And we did it. Woohoo! Yay us! All right. So, is our answer 7 plus h? No. What do we need to do now? Yeah, actually take the limit. And we get 7. See how easy that is? Now, by this time next week, you're going to look at this problem and say, 7. You'll just say, that's 7. And yes, you will. But that's next week. I'll make a couple of comments here. So when it comes to your algebraic tools that you'll need, there's not too many that you need to worry about, but I want you to make sure you can do the following. You should be able to expand, and by that I mean things like FOIL. So that's that 2 plus h quantity squared. You should probably also be able to factor. That sometimes does come in handy. So know how to factor. You should be able to add fractions. So assuming we have times, we'll do something with where we add fractions. So when I talk about add fractions, I'm talking about something like 1 over 3 plus h minus 1 over 3. How do you add a fraction here? What's the idea? What? Common denominator. Yes! That's the secret. But it's not a secret because we're telling you. Isn't it cool? We're not like, haha, we don't want you to pass this class. No, we want you to pass the class. We're going to tell you everything you need. There's one other thing that will come up, which is conjugation. Do you remember when do we use conjugation? Yeah. So if you see a square root, you're like, oh, I'm going to be doing conjugation. And pretty much that's it. These are the kind of algebraic tools. So it's like, okay, you have your definition, you plug in, and then you do your algebraic tools with the goal in mind to cancel some h's, and then after you cancel the h's, you plug in and you're done. So the process is not bad. It's only tedious. But like I said, we'll speed things up. In the interest of full disclosure, I will say for a quadratic, which this isn't a quadratic, if you have ax squared plus bx plus c, a, b, and c are arbitrary numbers, then f prime, I need a different symbol. I'll say at a point t will turn out to be 2a times t plus b. And you can go through the exact same procedure. We can check to see if that's true. Here, what would that say? Well, a is 1, b is 3. So you should get 2 times whatever number you plug in plus 3. Well, 2 times 2 is 4 plus 3 is 7. Yep. And like I said, it's a little bit faster once you have the tools. But, all right. Let's try another question. Or maybe a quick sort of sanity check. Suppose we have the following function. F of x is the absolute value of x. What is f prime of 0? Well, what do? You can just say, hey, there's a definition, right? It's the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. What's the top become? Well, good news is 0 plus h is also known as h. And the absolute value of h is? The absolute value of h.
0.
And then f of 0 is 0. And downstairs is h. So you have the limit as h goes to 0, the absolute value of h over h. What is that limit?
Well, that one would be negative 1, right? If you're going from the left side.
Ooh, someone is being very like, oh, if you come from this side. But if you come from that side. So, yes, you were saying? From the left, from the left. Yeah.
From the right, it would be positive 1, so the limit would make this.
Yeah, so if your h is positive, the absolute value does nothing. But if h is negative, you change the sign. So it turns out that this is negative 1 if h is below 0, and positive 1 if you're above 0. So picture-wise, we're asking the question about what's the limit as h goes to 0 of this expression where it's -1 from one direction, 1 from the other direction? Well, what's the limit? It does not exist. Because there's no consistency. You're getting different answers from the two sides. Oh, man. Well, that tells us that derivatives don't always exist. Okay, a little bit disappointing, but let's think about it in a different way. When we were after derivatives, we were saying, well, look, what are we really after? The slope of a tangent line. So let's think about this absolute value function. If I graph the absolute value, it looks like a V. Now, suppose I zoom in, because our sort of intuition is if you zoom in, you should start looking flat. So let's zoom in. If we zoom in, what happens? What do we look like? We look like a V. Well, maybe we just didn't zoom in enough. Okay, so let's really try this time. So we're really zooming in super close. What's going to happen? Yeah, it's still going to look like a V. No matter how much you zoom in, it's always going to look like a V at that point. So the intuition here is there isn't a derivative because the function isn't flat at that point. So it's possible that you can deal with functions which aren't flat at particular points. And so derivatives may not exist. In this case, I usually say, well, the problem is that the absolute value has a bit of a kink where there's a sharp bend at 0. And so the derivative doesn't exist. All right. Well, how are we doing on time? We're doing great on time. Plenty of time. Is there a question? We're doing, yeah, of course. Of course. Well, that just means we can keep going for as long as we want, right? All right. So that gets us back to our tangent line. And remember, what's the tangent line? It's that line that you see when you zoom in. And so the tangent line, it's the way I like to think about it, it's a line which is your best approximation to your curve y equals f of x near your point of tangency. Now, why do we say it's the best approximation? Well, essentially what's happening is your tangent line stores two pieces of information. And so how does it store your two pieces of information? It says it here, but I just want to write it down again. It stores the value of the function. And the way it stores the value of the function is it says, hey, what's happening at A? That point A, if your x-coordinate is A, your y-coordinate will be f of A. So your tangent line is storing the value of the function at A. And then it says, but I can do more. Because the line has essentially two things. It has like a slope and an intercept, so there's like two pieces of information. So it says one piece of information is I'll store the value of the function at that point. And then the other piece is I'm going to store the value of the derivative at that point, your instantaneous rate of change. So I have all this wonderful stuff right there at my disposal. So we can take an example. So suppose, and we'll just make up a line. Anyone have a favorite line? Y equals x. Let's make it more favorite than 0. No, that's less favorite. All right, I'll make up numbers here. 5x minus 6 is tangent to y equals f of x at x equals 3. Then, what can we say about f of 3? What can we say about f prime of 3? Which one of these is quick, and which one of these is also quick? You're trying to decide which one is. They're just both tempting to like say, I don't know which one to say first. Okay, one person says, I want to say f first. I want to say the derivative first. What's the derivative correspond to? It's your rate of change. And how's that stored in a line? Slope. So what's f prime of 3? 5. The tangent line at 3 stores your instantaneous rate of change at 3. Okay, what's the value of the function at 3? 9. Where does 9 come from? Yeah, you just plug in 3. Whatever the tangent line does at 3, the function does at 3 in terms of the value of the function. So you say, okay, 5 times 3 minus 6, and that's 15 minus 15 minus 6, which is 9. All right, so tangent line stores information. And there's a couple of ways to write tangent lines. So as we said, it goes through the point A, f of A, it has slope f prime of A. So there's the y minus your y coordinate is equal to your slope, f prime of A, x minus your x coordinate. You can also write it as y is equal to f of A plus f prime of A times x minus A. This is just moving the f of A across. And this is a great way to write it. It's sort of a hint of things to come in the future. And when I say the future, next semester, we'll come to a point and say, hey, remember tangent lines? I'm like, yeah. See, we're just doing that, but more. It's going to be a great time. Great time. I hope you'll be there with me. The other way, of course, you can write it is you can say, you can just multiply this out. Y equals f prime of A times x plus f of A minus a f prime of A, where this is your slope and this is your intercept. So this is called slope-intercept form. Whichever way you like, that's great, as long as you have it in some way. Okay. Let's see. We have a few things left to mention. We have some time. Should we try to find another tangent line? Yeah, we should try to find a tangent line. Here we go. So find the tangent line to y equals 18 over x plus 2 at the point x equals 1. So I got 8 minus 2x. Okay, so how do you do this? Now, the answer is, this is the long way to do this. This is only if it says using the limit definition do you go through this whole process. One of our goals is, and we're going to talk a lot about this at the end of the week, is to say, wouldn't it be nice if we didn't have to do limits all the time? Yes. So we're going to work to say, let's not do limits anymore. But we say, all right, we need the tangent line, which means we need the derivative and the value of the function. So the value of the function, you plug in 1. 18 over 1 plus 2, that's 18 over 3, which is 6. So we know it has to pass through the point 1, comma 6. 1 because that's our input, 6 because that's our output. So we say, all right, we just need f prime of 1. So we pull out the definition, plug in the function, do a little bit of simplifying, and say, okay, now in this case, what I would do is I'd clear fractions. Fractions scare me. So I'm going to multiply top and bottom by 3 plus h. And if you do that, no more fractions. And now I say, oh, this minus 6, when you distribute, you get 18, subtract 18, and you're like, oh, that's good. We've lived a good, clean algebra life, because we should get rid of constants. What we didn't get rid of is the minus 6 times h, but there's an h downstairs, so that h is canceled. We know we were shooting for this point where h is canceled. So now the h's have canceled, so we can plug in, and we have our slope. Slope plus point makes line. So there's our process. And life is good. All right, any questions on the process? Okay, let's try another one. We'll really more straightforward one, I hope. What about the following? Y equals sine 5x. And find the tangent line at x equals 0. Okay, so can you tell me about the point that our tangent line will have to pass through? What's our point? 0 for our x, but what's our y value? Also 0. Okay, so that's pretty good. Point is 0, 0. So what else do we need? We need a slope. So I'm going to call this sine of 5x. I'm going to call this f of x. So our slope, that'll be f prime of 0. Since we're still practicing, pull out the limit definition. Limit as h goes to 0. F of 0 plus h minus f of 0 over h. So what do you get when you plug 0 plus h into your function? Yeah, well, you can even simplify it. Say, I know that 0 plus h is just another way of saying h. So now, if f of x is sine of 5x, f of h is sine of 5h. F of 0? 0. And downstairs we have h. Okay, well that's good. Now we look at this limit and say, this looks familiar. Do we have ways of handling these limits? We start pondering, because we are ponderers. What do we start thinking about? Yeah, you have the limit. Someone said blah. I like that. Sine of blah over blah goes to 1. Do we have blah over blah? No. This has a 5. This does not have a 5. So what do? You put a 5. And I say, you can do that? Well, you can if you do what? Yeah, multiply the top by 5. You can put stuff in as long as you balance it out. So what's the limit become? Well, this part, it's now of the form sine blah over blah, goes to 1. What does the 5 do? It goes to 5. Or it stays at 5 if you like. So our limit is 5. So there's our slope. So we need a line which passes through the origin and has a slope of 5. What line does that? Y equals 5x. All right. So there we go. A few more notes. And I don't think we'll work through a whole problem, but I just want to make a couple of notes. You might have a question that says, find a line parallel. Okay, how are two lines parallel? Okay, good. So if you see something that says, find a line which is parallel, that means you have the same slope. You might also have a problem that says, find a line perpendicular, which is a harder word to spell. What does that mean? Well, what does opposite slope mean? It's like so opposite.
Negative 1 over the slope.
Yeah, so the fancy phrase is negative reciprocal. That seems very opposite. So for instance, if your slope was, say, 2/3, what's the negative reciprocal of 2/3? Negative 3/2. All right, so we have a few minutes left, and we should have enough time for our final cool down. Our multiple choice. 1 out of 5. Which of the following lines is tangent to y equals x squared plus x, and it perpendicularly intersects the curve x plus 3y equals 17? So there's a couple of choices. 3x minus y equals negative 2. 3x minus y equals 1. 3x minus y equals 3. 3x plus y equals negative 2. 3x plus y equals negative 6. Do we have an answer, or maybe some guesses? I heard B was the first one I heard, and that's bold, because it's right. It is 3x minus y equals 1.